In recent episodes, we've looked at the sad state of physics and astronomy. Our long-term heroine, Sabine Hossenfelder, has also been expressing concern about the same thing.
I've been worried about the problem with academic research ever since I became part of it about 20 years ago. Science is failing. It's failing right in front of our eyes, and no one's doing anything about it. My book is called Lost in Math. Unfortunately, people who haven't read the book sometimes think I'm saying that physicists use too much mathematics. Actually, what I say in the book is pretty much the opposite, namely that physicists don't take math seriously enough.
I came across this problem about 30 years ago. My son was studying physics with the University of South Africa. He brought a big fat textbook with some impressive mathematics and asked me to explain it. It was justifying a conclusion by starting from an abstruse equation, going through some mathematical manipulation and ending with the required result. He asked where that abstruse equation came from. I pointed out that the book gave no justification for it. But if you accept it, the manipulations lead to the desired answer. He was so disillusioned, he dropped physics and turned to business administration.
I'm pointing out that there's no progress in the foundations of physics. It's a fact. We haven't made progress in theory development for 50 years. We still use the quantum field theory of the Standard Model, which dates to the 1970s, and we still use general relativity, which is more than a century old.
And here, I think, we get to the heart of the problem. She's so imprisoned in the paradigm, she can't see that relativity has been the biggest disaster in the history of science. Where did it come from? It came from the fanatical search for refutation of all the evidence that the Earth is at the centre of the universe. This strange theory did not prove that the Earth is not at the centre. It simply claimed it was impossible to tell whether it was moving or stationary. It was not even a convincing theory, as we saw in episode 72. Louis Essen called it a number of sometimes contradictory assumptions. Harold Nordenson said, "It is not physics but philosophy, and in my opinion, poor philosophy." Tesla likened it to a beggar, clothed in purple, whom ignorant people take for a king. And as Rutherford put it, it's simply nonsense. Even Einstein abandoned it little by little. He denied that the speed of light was always constant, not much more than a year after he published the special theory. He told us that general relativity was unthinkable without ether not long after he published the general theory. But the possibility that all the clear evidence that the Earth was stationary had not been refuted was so horrifying that everybody stuck their fingers in their ears and kept going with relativity anyway. Minkowski's four-dimensional space-time, with its mathematical dimension of imaginary time multiplied by the speed of light, became the platform for the quantum story with its imaginary wave functions. The rational platform, three-dimensional space with Lorentz and Maxwell's ether, was shunned. So instead of worthwhile theory development, we have thousands of worthless PhDs and hundreds of thousands of valueless papers dealing with pipe dreams.
Ultimately, I don't know what caused the problem. I can only speculate. But it's not a speculation that we do have a crisis in the foundations of physics. It's a fact that we haven't made progress with theory development for 50 years.
About 100 years ago, Einstein added a variable to his equations of general relativity to represent the energy infused in space itself. He called it lambda, or the cosmological constant. In 1998, teams led by Adam Rees, Saul Perlmutter, and Brian Schmidt confirmed the presence of dark energy, winning them a Nobel Prize in 2011. The discovery matched Einstein's hypothesis about an accelerating universe and a cosmological constant. But in April 2024, data from a new telescope instrument produced the biggest map of the cosmos yet. The results throw the cosmological constant into question, suggesting that dark energy might be changing.
That would not be what a cosmological constant would have been predicting.
This opens the floodgates for new theories. To understand what the cosmological constant is, we have to sort of start at the beginning, which is the Big Bang. There's this initial kick of energy and the universe starts expanding outwards. The dominant force is, generally speaking, gravity. We would expect that because it's filled with matter and dark matter, the universe would eventually slow down because of this attractive force due to gravity. But not only is it not slowing down, it's accelerating. That's akin to me on Earth throwing up a tennis ball, expecting it to come back down due to gravity, and it doesn't. It keeps going up and it's accelerating upwards.
The simplest explanation for this acceleration is Einstein's cosmological constant, an unchanging dark energy that permeates empty space.
The universe is expanding. We're essentially getting more and more empty space between galaxies and consequently more and more dark energy.
This hypothesis is the basis of lambda CDM, cosmologists' current model of the universe.
Physicists and cosmologists are between a rock and a hard place. 95% of the energy and matter in that model we cannot fully explain.
In 2021, the Dark Energy Spectroscopic Instrument, known as DESI, kicked off a 5-year effort to measure the positions and velocities of 40 million galaxies.
The goal of DESI is to build the largest 3D map of the universe that we've ever achieved.
If you want to measure and understand dark energy, you want to look at the universe at its largest size. DESI has 5,000 optical fibers that allows the instrument to collect 5,000 galaxies at a time.
As DESI's fibers collect light from galaxies, a spectrograph splits the light into its individual wavelengths. This reveals how quickly a galaxy is moving away from Earth, which the researchers use to infer its distance. But to measure the expansion rate of the universe, DESI scientists turned to baryon acoustic oscillations, or BAOs, the leftover imprints of pressure waves from the Big Bang. Each of these unique features is imprinted on the universe like a ripple frozen onto a pond.
And the only thing that changes its size is the expansion of the universe. So with DESI, by measuring this 3D map of the universe over time, we can actually see how BAO has evolved over time, and therefore the impact of dark energy on that expansion.
If dark energy were the cosmological constant, galaxies would appear to be accelerating apart at an unchanging rate. But DESI showed that in the universe's most recent history, many galaxies appeared closer together than expected, suggesting that dark energy is weakening over time.
This is not at all what we were thinking that we would be obtaining with this first-year results. So that was an amazing surprise. If we confirm that dark energy is varying with time, then it just is not compatible with lambda CDM.
In episode 77, Thomas Kuhn warned us that a scientist's professional training, or indoctrination in the accepted paradigm, leads to research becoming a strenuous and devoted attempt to force nature into the conceptual boxes supplied by professional education. We also saw that even Christian scientists are so indoctrinated with relativity they can't believe what the Bible clearly says. So it shouldn't come as a surprise that most secular humanists can't see the obvious failure of Einstein's fairy tale. And when they notice features they had never expected, they've become masters at what Brad Schaefer called instant science, inventing plausible stories based on a lack of observational evidence, like baryon acoustic oscillations. They're soon so convinced that their speculations must be right that they become standard parts of the theory. But surprise, surprise, after all the evidence coming from the James Webb Telescope, some people are starting to realise that there are flaws in the Big Bang story. The Big Bang stories come from the general theory of relativity, and some renegades are starting to point to cracks in the whole story.
What if the very signal that we think proves the Big Bang didn't come from the Big Bang at all? Modern cosmology is built on a framework, one that's constantly being patched. CMB fluctuations too smooth, we introduce inflation. Galaxy rotations don't add up, we add dark matter. But what happens when one of those patches, instead of fixing a small inconsistency, breaks the whole system? To explain the massive, fully formed galaxies seen in the JWST, cosmologists assume they must have formed incredibly fast, faster than they ever thought possible. But now, a mainstream paper argues that all that early light, processed by dust, stretched by redshift, could account for a large part, if not all, of the CMB, which means that the very thing that we treat as a snapshot of the Big Bang might actually come from galaxies. And if the CMB isn't a relic of the early universe, everything starts to unravel. To understand how we got here, we have to follow the loop. First, the James Webb Space Telescope revealed something unexpected. Massive, fully formed galaxies appearing far earlier than predicted, some just a few 100 million years after the supposed Big Bang. This shouldn't be possible. There simply isn't enough time in the standard model for galaxies that large to form by then. So, cosmologists introduced a fix. Perhaps these galaxies formed incredibly fast, with extreme star formation rates and a skewed population of massive stars. A top-heavy initial mass function. That patch worked, at least on paper, but it did have a side effect. More stars forming faster means vastly more radiation. The radiation, reprocessed by dust and redshifted by cosmic expansion, created a diffuse background glow. And, according to the new paper, the total energy of that glow could match the cosmic microwave background, the CMB. In other words, the fix for early galaxies created a new source of background radiation, and that source could be strong enough to account for the very signal we've been calling the relic of the Big Bang. So now we're stuck in a loop. JWST sees early galaxies, model breaks, rapid formation is assumed, increased radiation, explains the CMB, but the CMB is used to anchor the timeline that defines what counts as early. It's circular. The solution to one problem becomes the foundation for another, and the line between cause and consequence disappears.
Long before the Big Bang was thought of, scientists like Arthur Eddington reasoned that the energy from stars shining on interstellar dust should lead to a background temperature everywhere of 2 or 3 degrees Kelvin. When the Big Bang was becoming the latest fashion, Robert Dicke, Jim Peebles and David Wilkinson calculated that the Big Bang should have produced an echo or afterglow. Its temperature should have been about 50 degrees Kelvin. Arno Penzias and Robert Wilson tried out a microwave detector just to see what they would find. They found a uniform microwave signal of about 3 degrees Kelvin wherever they pointed their detector. They wondered what it could mean. After a while, Dicke, Peebles and Wilkinson heard about it. They decided this must be their echo or afterglow. It was more than 10 times the 3 degrees Kelvin, but that was swept under the carpet. The world accepted it with joy. There were plenty of other ways it didn't fit, but those problems were swept under the same carpet. It became an accepted fact that this was the absolute proof of the Big Bang.
This paper reopens the question. It shows that if galaxies formed early and intensely, as current observations seem to demand, then the same process could naturally generate the background radiation we've always attributed to the Big Bang. Not as a leftover, not as a relic, but as an ongoing process. It suggests we may have been seeing this glow all along, not as the beginning of time, but as the signature of galaxies lighting up the sky. So what exactly did the authors of this new paper do? They started with a simple but powerful idea. If early type galaxies, the massive elliptical galaxies we see even at high redshifts, formed rapidly, then their combined radiation output must have been immense. To quantify that, they assumed a high star formation rate on the order of thousands of solar masses per year, consistent with what's required to explain the Webb observations. They adopted a top-heavy initial mass function, meaning these galaxies would have produced far more massive stars than normal, burning brighter and dying faster. These stars flooded the surrounding with energy, much of which would have been absorbed and re-emitted by interstellar dust. That processed radiation would then be redshifted as the universe expands, stretching it into the microwave band. So the authors asked a simple question: how much energy would that process contribute to the present-day radiation field? The result is striking. Depending on how closely packed these early galaxies were, that is, how much of the sky their re-radiated light would have filled, the authors estimate that this process could account for anywhere from 1.4% to 100% of the CMB's energy density. Not a minor foreground, not a small correction, but potentially the entire signal. If the CMB isn't primordial, then our entire understanding of the universe's timeline begins to fall apart. In standard cosmology, the CMB marks a fixed point, a thermal snapshot of the universe just 380,000 years after the Big Bang. That moment becomes the foundation for nearly every calculation of cosmic age, distance, and evolution. But if that radiation is not a fossil imprint, if it's just reprocessed light from early galaxies, then the foundation cracks. And here's what falls. Redshift would no longer map cleanly to the time since the Big Bang if the anchor point used to calibrate it was wrong. The cosmic ruler used to measure large-scale structures is partially defined by the CMB. Without it, distance ladders lose a rung. We would no longer know when expansion began, or if it began at all. If what we're calling early galaxies are actually common features of a non-expanding or differently evolving universe, the entire temporal history needs to be re-evaluated. Without a CMB relic to point to, the idea of a hot, dense early origin may become just one interpretation among many, not a settled fact. And the problems don't stop there. Baryon acoustic oscillations, often described as fossil sound waves from the early universe, also rely on the CMB being primordial. These patterns in galaxy distributions are only meaningful if they originated in a dense plasma before photons decoupled. But if there was no primordial CMB, those ripples may not be relics at all. They may just be natural patterns, emergent structures in a maturing cosmos. In that case, we're not seeing echoes from the beginning of time, we're just seeing the universe organizing itself. From there, the rest begins to fall. The justification for dark matter, especially the quantities inferred from the temperature fluctuations and the BAO, becomes far less convincing. The case for dark energy, introduced to explain an accelerated expansion needed to form structures quickly, weakens if that timeline is wrong. If the CMB isn't a relic, if it's just light from galaxies, then the Big Bang isn't just wounded, it may never have happened.
And even our heroine Sabina seems to be struggling a little with her hero Albert's mythomagical space-time.
It seems to strongly suggest that indeed space and time don't actually exist, but that they are just our way of describing an entirely relational network of something else. It makes my head spin when I think about this. I mean, it's hard enough to get used to a 4-dimensional space-time and deal with the question of what space and time really are. But now maybe neither space nor time exist. I'm not sure my brain is quite ready for this.
They received not the love of the truth, that they might be saved. And for this cause God shall send them strong delusion, that they should believe a lie. Thank you for joining me for this episode. If you enjoyed it, please like, subscribe and press the bell so that you'll be notified as I release new movies. If you'd like to support this project, you're welcome to do so through Patreon. Find a link on my channel banner and in the description below.